Okay, this is section 4.2. We're going to talk about a really important theorem. It's called the Mean Value Theorem. And before we get to the Mean Value Theorem, we have to talk about another theorem. It's called Rolle's Theorem. Now, again, you should have my notes in front of you, or at least on your screen. I'm not going to write it up here. So it says, let f be a function that satisfies the following three hypotheses. Okay? F is continuous on the closed interval a to b. F is differentiable on the open interval a to b. Now, the reason why we have a closed interval and then an open interval is because we only care about a continuous function on a closed interval. So then we say it's differentiable on the open interval because at the end of this function, we don't know, there could just be a sharp point like that. It could just bounce and just be like that. Let's see, here's another sharp point like that. Okay? So we don't know anything beyond on the outside of the function, so we cannot necessarily say that it's differentiable at the endpoints. So that's why we only need to be continuous on the closed interval and differentiable on the open interval. And then we have another last condition, f of a equals f of b. Okay? So it means the endpoints of the interval, the values of the endpoints of the interval, are the same number. Okay, so if all three of those hypotheses are satisfied, then there is a number c in that open interval a to b such that f prime of c must be equal to 0. Okay, so there are three cases of this. See, right there's A, over there's B. Let's say f of x is equal to k, where k is a constant. So, right there's k, and on this closed interval, let's go ahead and talk about the three hypotheses of Rolle's theorem. The first one, that it is continuous on the closed interval a to b. Now, it's a constant function. It's just a horizontal line going through k, whatever k is. It's just a number. It is definitely continuous. Is it differentiable? Well, yeah, it's differentiable. It's just a number. The derivative of a number is 0. The slope of a horizontal line is 0. So, it's continuous, it's differentiable, and now f of a, well, that's equal to k. Any x value, it's equal to k. And f of b is equal to k. So the final hypothesis is satisfied. F of a equals f of b. So then, Rolle's theorem says there exists a c such that f prime of c is equal to 0. And in fact, this is the really easy case that c happens to be any number between a and b, because everywhere has a slope of 0. Okay? So let's look at another case. Right here's A, right there's B. So right here's f of A, right there's f of B. As you can see, they're exactly the same. They're on the same horizontal line, whatever this number is. We can call it k again if you'd like. So, to see that this satisfies the mean value theorem, the Rolle's theorem, well, f of A is equal to f of B. This is definitely continuous, and it's definitely differentiable, okay? It's nice and smooth. It doesn't have any corners. There's no asymptotes or anything. So that says all three hypotheses are satisfied, then there exists some number C right there such that f prime of C must equal 0. And if we were to draw a horizontal line right there, we got a horizontal tangent, which we know horizontal tangents have a slope of 0. Now there's a third case of this. Let's say f of A is right there. F of B is right there. So we have something like that, okay? Now we could say our C value's right there, right here. At f prime of C, it's equal to 0 because we have a horizontal tangent right there. So what the mean value theorem is saying is if you start at some level and you end at the same level, so right there, f of A is equal to f of B, if you're on a continuous function, somehow you got to end up back over there, then you must reach some maximum. Or you go the other way, you have to reach some minimum. That's really what Rolle's theorem is saying. Now let's do an example. It says verify the function, here's our function, is equal to sine of x over 2 on the interval pi over 2 to 3 pi over 2. Verify that this function satisfies the three hypotheses of Rolle's theorem on the given interval, then find all the numbers C such that that satisfy the conclusion of Rolle's theorem. So we need to find where f prime of C equals 0. What C values make that true? Alright, the first thing I'm going to do, the third condition is probably the easiest to satisfy. First find f of pi over 2, which is sine of pi over 2 divided by 2, which is sine of pi over 4, which we know is root 2 over 2. Now let's find f of 3 pi over 2, which is sine of 3 pi divided by 2 divided by 2, which is sine of 3 pi over 4, which also happens to be root 2 over 2. So, if this is our A and that's our B, we do indeed have f of A equaling f of B, which is equal to root 2 over 2 in this case. So that's the third condition of Rolle's theorem, that f of A has to be equal to f of B. You could have done this on a calculator and easily got the result. Alright, so now let's talk about the other two conditions. If you think back to chapter 2, we talked about continuous functions. Sine is continuous on its entire domain, negative infinity to positive infinity. So of course it should be continuous on any closed interval within that domain. Not only that, it is also differentiable on its domain from negative infinity to positive infinity. So any closed interval, open interval from pi over 2 to 3 pi over 2, it is differentiable there as well. So that's hypothesis 1, hypothesis 2. We already did hypothesis 3. So now Rolle's theorem guarantees that there is some c value that makes this equation true. So let's go ahead and find the derivative, plug in c, set it equal to 0, and solve for c. So f prime of x is cosine of x over 2 times the derivative of the inside, which is just 1/2. So now I'm going to plug in c and set it equal to 0. So I got 1/2 cosine x over 2 is, c over 2 is equal to 0. I could divide both sides by 1/2. And you get cosine of c over 2 is equal to 0. I'll write it over here. Cosine of c over 2 is equal to 0. So now I got to think to myself, where does the x value, at what angle does the x value equal 0? So we have c over 2 is equal to, well, one place that cosine of c over 2, or cosine is equal to 0, is pi over 2. Let's see, c over 2, another place cosine is equal to 0 is 3 pi over 2. So it just so happens to be the endpoints of our intervals. Now, we need to solve for c, so I gotta multiply this by 2, multiply this by 2, multiply this by 2, multiply this by 2. And I got c is equal to pi. And I also got c is equal to, those two's cancel, 3 pi. Now, these are all the numbers that would, where the derivative is going to equal 0. However, look at the interval that we're on. We're on the interval from pi over 2 to 3 pi over 2. If I were to draw this on a unit circle, here's pi over 2, and here's 3 pi over 2. We're on this part of the unit circle over there. 3 pi is indeed right there in that area. However, that's in a different period. So this right here is not the c value that we're interested in. However, this value here is pi. This right here is the c value that will guarantee that our derivative is equal to 0. That was the second part of the problem. Then find the number c that satisfy the conclusion of Rolle's theorem. Okay, there it is. Okay, so there's another problem you should try. It's doing the same thing. You have a polynomial there. That solution will be posted on Blackboard, so go ahead, pause the video, take a moment, try it, pull up the solution, check your answer. And now we're going to go through another example. It says, let f of x equal 1 minus x to the 2/3 power. Show that f of negative 1 is equal to f of 1, but there is no number c in the open interval negative 1 to 1 such that f prime of c is equal to 0. And then they ask a question, why does this not contradict Rolle's theorem? Alright, so First thing, show that f of -1 is equal to f of 1. This is really easy to do here. So f of 1 is equal to 1 minus, well, 1 to the 2/3 power. 1 to any power is equal to 1. So this is 1 minus 1 is equal to 0. F of -1 is equal to 1 minus -1 to the 2/3 power. This is also going to be 1. To see how it's 1, it's -1 squared. Let's forget about this cubed root right here. -1 squared is positive 1. Positive 1, this denominator of 3 is a cubed root. The cubed root of 1 is 1. So we get 1 minus 1 again, which is equal to 0. So there, we just verified that one. Okay, so let me go ahead and let me go ahead and erase this. Let me keep the function up here though. Alright, so this function right here, it is continuous on its domain. I have my calculator somewhere. Oh, here it is. Let me show you the graph of this thing. 1 minus x to the 2 divided by 3. You could also plug this in on your calculator and get a better view of it. It goes something like that. And if you were to restrict yourself from -1 to 1, it's going to look something like that. So, it's definitely continuous on its domain, the one we're talking about from -1 to 1, the one the problem talks about. Now, the only issue is the second condition, which says f is differentiable on the open interval from, in this case, -1 to 1. Is it differentiable on this interval? The answer is no, it is not differentiable. We have a sharp point right there, okay? Now, if we were to take the derivative of this, f prime of x is equal to, well, derivative of 1 goes away, we have a negative sign, okay? And then the 2/3 comes out in front, x, and then subtract 1, so we get a -1/3. So I'm going to rewrite this as -2 divided by 3, and then this is a cubed root of x. As you can see, at 0, if I plug 0 into here, it's a bad number. The derivative doesn't even exist. F prime of 0 does not exist. Not only that, if we were to try to take this function, -2 over 3 cubed root of x, set it equal to 0, since it's a rational function, the only way a rational function can be 0 is if the numerator is 0. Well, the numerator is -2. Is -2 ever 0? It is not. So we cannot find any critical numbers. So therefore, Rolle's theorem is not contradicted because we don't satisfy the second condition. Okay, the first condition's good, the third condition's good, but the second condition, f is differentiable on the open interval a to b, is not true. Okay.